We all rely on infrastructure, right? Every single day.
Yeah.
Roads, buildings, the foundations holding everything up.
Absolutely. Crucial stuff.
But sometimes, beneath all that, there's this hidden challenge, soft clay.
Mm-hmm. A big one in many places.
Think about a highway that just keeps cracking, needing repairs all the time, or maybe a big construction project that seems to, well, sink.
Yeah, slowly giving way. It happens more than you'd think.
And it's not just annoying, it's a huge cost. Billions, actually, every year.
Yeah.
Especially with soils like Batu Pahat soft clay, BPSC, you find it in places like Malaysia, for instance.
That's spot on. And the real problem with BPSC, it boils down to its basic properties.
Okay. Like what?
Well, it's got this really high plasticity
Mm-hmm.
and very low strength, what engineers call shear strengths.
Low strength, right. Not good for holding things up.
Not at all. Plus, often incredibly high moisture content, sometimes over 80% water.
Wow, 80%, that's mostly water.
Pretty much. And those aren't just, abstract terms. They mean real trouble. Big settlements, damage to structures, roads.
And those huge maintenance bills we mentioned earlier?
Exactly. Those relentless costs. It adds up fast.
Okay, so the problem's clear. And it's expensive. Now, traditionally, how did engineers tackle this? Like, what were the go-to methods?
Well, the classic approaches involve things like physically removing huge amounts of the soft soil and just replacing it with better material.
Dig and dump, basically.
Essentially, yes.
Yeah.
Or using traditional stabilizers, mainly lime and cement, often in very large quantities.
Right, I've heard of using cement. But you mentioned downsides. These aren't perfect fixes, are they?
No, not by a long shot.
No.
While they can work, these methods are incredibly resource heavy. Think of the cost, the energy, hauling all that material around.
Yeah, that sounds expensive.
It is. And maybe more importantly today, they have a pretty significant environmental impact. High carbon emissions, especially from cement production.
Ah, the CO2 factor.
Exactly. Which is why there's such a push, to find better, more sustainable alternatives.
And that brings us perfectly to our deep dive today. For you listening, we're exploring a really innovative, sustainable solution using something called biomass silica and sodium silicate.
Mm-hmm.
And the research we're looking at doesn't just ask if it works, but digs into how it fundamentally changes the soil, right down to the microscopic level.
That's the fascinating part, understanding the why.
So let's unpack this BPSC a bit more. What specifically makes it such an engineering headache? What's it made of?
Okay, so BPSC, its composition is key. It's mostly fine-grained stuff. We're talking about 36% clay, 61% silt.
Mostly silt and clay, then.
Exactly, only about 3% sand. And that makeup is precisely why it's so compressible, why it squishes down, and why it has that low shear strength we talked about.
So it just can't support much weight without settling?
Pretty much. Any significant load, like from a building or heavy traffic, can cause major settlement over time. Plus, it's really sensitive to water. Changes in moisture content make it swell or shrink, and water drains through it incredibly slowly. Both of those things make construction tricky and affect long-term stability.
Okay, I see. So that directly leads to those cracked roads and building foundation problems.
Directly. It's all connected back to those core properties.
The stakes are definitely high then. Safety, cost. And the old ways aren't ideal, which I guess leads us to the really interesting part, this new approach.
The sustainable alternative, yes.
Tell us about these materials. Biomass Silica, SH85, I think you called it, and Sodium Silicate, TX85. What are they, and why are they potentially such a breakthrough?
Right. Let's take them one by one. Biomass silica, the SH85, it acts as a pozzolanic material.
Pozzolanic. What does that mean in simple terms?
It basically means it reacts with calcium hydroxide, sometimes naturally in the soil, sometimes added to form cement-like compounds, calcium silicate hydrates or CSH.
Ah, like a binder, a glue.
Exactly. The glue that holds soil particles together makes it stronger, and the biomass part is key for sustainability.
Because it comes from...
Often from agricultural waste. Things like rice husk ash. So instead of landfill, you're using waste. And you're avoiding the CO2 emissions from making traditional cement.
Okay, that's clever. Using waste to build strength. What about the other one? Sodium silicate, TX85.
Sodium silicate, or TX85, works a bit differently but complements the SH85. It helps enhance the bonding between the soil particles themselves.
Okay.
It reacts with the silica and alumina that are already naturally present in the clay, forming these strong sort of matrix structures within the soil.
So it reinforces the soil structure itself.
Precisely. And a big plus is it can often lead to faster strength gain and makes the soil more resistant to water, which means you might need less or even no traditional cement.
Less cement is definitely a win for emissions. Now, the research we're diving into looked at combining SH85 and TX85. Why put these two together? What's the idea there?
That's a really important point. It's all about synergy.
Synergy, meaning they work better together than apart.
Exactly. Much better. When you combine them, they seem to accelerate those pozzolanic reactions we talked about, the glue-forming ones.
Ah, so it speeds things up.
Speeds things up and creates a much more robust, stronger soil matrix overall. You get greater strength, better durability than you would using just one of them.
And this combined effect, especially on tricky soils like BPSC, wasn't really understood before this research.
That's right. It was a significant research gap. People had looked at them individually, but how they worked together in this specific context wasn't clear.
Okay, makes sense. So for you listening, how do scientists actually prove this works? When they do a deep dive like this, what kind of tests are we talking about?
It's quite a comprehensive process, really. They look at it from, well, two main angles: the big picture engineering properties and the tiny microscopic details.
Macro and micro, got it. What are the macro tests?
Those are things engineers routinely use, like unconfined compressive strength UCS. That basically tells you how much pressure the soil can take before it, well, fails or collapses.
Okay, it's crushing strength.
Sort of, yes. And the California bearing ratio, or CBR, that's a really common one for roads. It tells you how suitable the soil is as a subgrade, the layer beneath the pavement.
Right, needs to be strong enough.
Exactly. They also do compressibility tests to see how much it's likely to settle under a load.
And the micro level, what tools do you use to see what's happening down there?
That's where it's really interesting, I think. They use techniques like X-ray diffraction, XRD, and FTIR spectroscopy.
Okay, fancy names. What do they tell you?
They help identify the new chemical compounds that are forming inside the soil because of the treatment. Are those cement-like CSH compounds actually there? These tests can show that.
So chemical proof.
Yes. Then there's scanning electron microscopy, SEM. This gives you actual pictures, images of the soil structure at a microscopic level.
You can actually see the difference.
Absolutely. You can see if the particles are packing together more densely, if the structure looks more solid compared to the untreated clay. It's visual evidence.
Cool. Any others?
Yeah. They also use EDX, energy dispersive X-ray analysis, which tells you about the elemental composition, what atoms are where, and simple pH tests to track chemical changes. It all builds a picture.
And surely how long these effects last is critical. A quick fix isn't much use for a highway.
Oh, absolutely critical. You need long-term performance. So the study didn't just test immediately. They looked at samples after different curing times.
Curing like concrete, letting it harden.
Exactly. They tested it 7 days, 14 days, 28 days, and even out to 90 days.
3 months.
Right. That extended testing is crucial to confirm that the strength and stability gains are durable, that they'll hold up over time in a real-world structure. Gives you confidence.
Okay, so they did all these tests, macro and micro, short-term and long-term. What did they find? Did this SH85 and TX85 combo actually deliver for Batu Pahat soft clay?
It really did. The results were quite striking, actually. First off, they pinpointed the best recipe, the optimal mix.
The sweet spot.
Yeah. It turned out to be 3% sodium silicate, that's the TX85, which they called 3L, combined with 9% biomass silica, the SH85, called 9P.
3L and 9P. Okay.
Finding that optimal blend was a key result in itself. And that specific combination led to some dramatic improvements.
In the engineering tests?
Yes. Big increases in both UCS, the compressive strength, and CBR, the bearing ratio. Really significant jumps.
How significant? Like enough for practical use?
Definitely. The treated soil actually exceeded the minimum CBR value needed for a road subgrade. That threshold is typically around 12%. This mix got it well above that.
That's a big deal for road build.
A huge deal.
Yeah.
And they also saw that the CBR value kept increasing with longer curing times, 28 days, 90 days, showing the strength gain that wasn't just immediate, it continued to develop.
It gets stronger over time. That's good. What else?
They looked at stability using those Atterberg limits we sort of touched on, the tests that measure how soil behaves with water.
Right, the plasticity stuff.
Exactly. And they found the liquid limit went down, the plastic limit went up, and the overall plasticity index decreased.
Okay, translate that for us. What does that mean practically?
It means the treated soil became much more stable, less mushy when wet, less brittle when dry. It's far less sensitive to those moisture changes that cause swelling and shrinking problems.
Ah, so more reliable, less movement.
Precisely. A really big win for preventing long-term damage. They even observed the particle sizes changing, shifting from mostly clay towards silt-sized particles after treatment. a fundamental change.
And did it settle less? The compressibility?
Yes, significantly reduced compressibility and also less swelling potential. So less settlement under load, which is obviously critical for foundations and roads.
So the big picture engineering properties looked great. Did the micro level tests back this up? Did they see why it was getting stronger?
They did, and that's what makes the study so convincing. These SEM images, the microscopic pictures, they clearly showed denser structures forming. You could visually compare untreated loose clay with the treated soil, which looked much more tightly bound.
You could see the glue working.
You could literally see the effect of that glue. And the chemical tests, FTIR and XRD, confirmed what the glue was. They detected the formation of those cementitious compounds, the CSH, that we know are key for strength.
So the chemistry matched the pictures and the strength tests.
Perfectly. And other tests like pH changes and the EDX elemental analysis further supported that these chemical reactions were happening, transforming the soil. It all lined up.
Wow, so it's not just like mixing sand into mud. It's a real chemical and physical transformation happening at a tiny scale, but with huge effects.
That's exactly it. It's a fundamental alteration of the soil's properties.
So what does this tell us about the actual mechanism? How does this combination work its magic?
Well, pulling all that evidence together, the research essentially confirms a stabilization mechanism that involves a few key processes working together. There's cation exchange, there's flocculation, which is like getting particles to clump together, and then those crucial pozzolanic reactions creating the cement-like bonds.
So it's a multi-pronged attack on the clay's weaknesses.
You could put it that way, yes. It provides a solid scientific explanation for how these specific materials interact with this specific type of soil to make it strong and stable.
This deep dive really shows a powerful solution. Stepping back from the science for a moment, what are the bigger real-world implications? Why should our listener care about stabilizing BPSC this way?
Well, the practical relevance is enormous. For engineering, it's a potential game changer.
How so?
By boosting soil strength, increasing its load-bearing ability, reducing that settlement, it means we can build much more durable infrastructure. Roads that last longer, foundations that don't sink.
Which means less money spent on repairs.
Exactly. A massive reduction in those multi-billion-dollar annual maintenance and rehabilitation costs. Think fewer potholes, less construction disruption, safer structures.
Yeah.
That benefits everyone.
Okay, cost savings, better infrastructure. What about the environmental angle you mentioned earlier?
That's the other huge benefit. This is genuinely sustainable construction. You're taking biomass waste stuff that might otherwise rot in a landfill, releasing methane.
And turning it into a building material.
Precisely. Upcycling waste into a valuable resource. And crucially, it offers a low-carbon alternative to relying so heavily on cement.
Right, cutting down those CO2 emissions.
Which is vital for meeting climate goals. So it's not just good engineering, it's good environmental stewardship. It aligns perfectly with the need for greener construction practices.
It really is amazing when an engineering fix also delivers such clear environmental wins.
It's the ideal outcome, really. Solving a problem while also helping the planet.
So we've taken quite a journey here deep into the ground beneath us, exploring how these tricky soft clays pose a challenge, but also how innovative science, using biomass silica and sodium silicate, can offer a sustainable fix.
Yeah, and it really underscores how valuable it is to look at things on both the big scale, the engineering performance, and the tiny scale, the microstructural changes. Understanding both is key to unlocking these kinds of solutions.
Solutions that are effective, but also responsible. Turning waste into strength, as you said. This whole deep dive definitely gets you thinking. So here's a final thought for you, our listener, to maybe chew on.
Yeah, think about this. What other big problems out there, maybe in totally different fields, not just engineering? What problems might be solvable if we look differently at materials we currently consider waste?
Or if we explored the unexpected power of combining different substances, understanding how they interact at that fundamental, maybe even microscopic level.
Could the next breakthrough be hiding in an unlikely combination or in something we're currently throwing away?
Food for thought. We hope this deep dive has given you a new appreciation for the hidden complexities under your feet and for the clever ways science is working to build a more stable and sustainable world for all of us.